Our objective is to design a compressed air water rocket system to maximize the duration of a payload if an egg is held aloft. In order to do this, we had to find the best water fraction for thrust, location and size of the fins for stability, parachute and nose cone size, and how all these elements would come together for optimum design in different weather conditions.
The thrust is provided by the release of the reaction mass, which in this case is the water in the water rocket. Thrust occurs because of the difference in atmosphere pressure created inside the water rocket when compared to the natural surroundings. At a water fraction volume of 0 and 1, the rocket fails to launch. At a water fraction volume of 0.75, the parachute didn't open until the rocket landed. It's obvious that when the water fraction is 0.25, the performance of the rocket is the best.
Directional stability is the capability of an aircraft to return to its original flight direction after going off course and is affected by fin placement and shape. As seen here, placing fins high on a rocket makes it unstable. As you can see in the second clip, stability increases by lowering the center of pressure, but if the fins are too low, the rocket may be too stable and not allow time for parachute deployment, so a balance must be struck when placing the fins and creating their shape.
The main challenge is to find the optimum parachute size. Starting from a small nose cone and a small parachute, progressing to a small nose cone and a big parachute. The simulation showed that if the parachute is too small, there wouldn't be enough drag force to slow down the descent. And if the parachute is too big, center of mass would be too forward, causing the rocket to flip. Realistically, our nose cones won't be long and pointy, even though the simulation showed that a big nose cone and a big parachute would give the best time with the center of mass rather aft. It would not be implemented. We have found that a 40 cm diameter medium-sized parachute and a medium-sized nose cone wouldn't cause flipping and would slow down descent sufficiently.
Rocket build quality is crucial. Misalignment of the center of pressure at the center of gravity causes unwanted moments, as shown on screen. Mass, drag, thrust, stability, and build quality must be optimized for an increased flight time. Design is constrained by the risk assessment. The nose cone must be at least 1 centimeter in diameter, for example. The following clips show that 4 fins are the best choice when mass, drag, and build quality are considered. A rocket with 3 fins is more streamlined but less stable.
Weather affects a rocket's trajectory. Calm wind has little effect on trajectory as shown. Light wind only slightly deviates the path. This is avoided by making a stable rocket with a center of lift behind the center of gravity. Strong wind affects trajectory significantly as shown next. To avoid the rocket making touchdown out of bounds, launch at an angle.
In conclusion, we found that these aspects of rocket design were the most important to help achieve our design objective.